can talk about Chow variety. Let's welcome.
So I'll just give you a very short introduction on Chow variety. And I will mainly focus on characteristic zero theory, and then also if I have time, I'll just mention some taxonomy in plastic characteristic, which is not going to be needed in this paper, but I think it's some nice thing you probably want to know. So let's start with some notation. So I fix x. So let's say it's projected. And then that's over, let's say over C, or heuristic K is 0. So later I'm going to remove this this condition, but for now let's just do this. And let's fix an M4 line bundle. Okay, so now we are going to talk about all possible cycles in X with positive dimension d prime and with degree d. So I pick two numbers. D prime is going to be the dimension of cycle, and then d is going to be the L degree of cycle. So I'm going to write as a formal sum. The cycle is going to be written as this way. Just write this. So this is some natural number, and in here is some vi, and vi is dimension d. And I'm going to assume it's reduced because I just take this sort of the building block. So I'm just going to assume it's reduced, and you reduce it. One space. And as you can imagine, I'm going to fix the dimension to be d prime because I normally use reserve d for degree, so unfortunately that's a little bit weird. And I'm going to make the L degree to be d, so that just means if I take the L degree on each vi, and because I assign multiplicity ai for each vi, so I have one. So that's the natural L degree on a d-dimensional variety, and then together to be d. And as we assume L is ample, so this guy is going to be some positive number. And so that's only possible, finding many possible selection of this AI to make D. And now the main issue is
So is it the definition for being D being an L degree of cycle?
yeah, so I'm just give you one member of D prime dimension cycle with L degree D. It's just some possible combination of dimension D prime thing, and then you want the degree to the total degree to be D. Let me start with
That meant by the L degree.
yeah. I mean this guy. So when you compute degree, you need to raise it to the suitable power and then do the integration.
Should that be D prime?
Oh, D prime. Okay, so let me start with some simple example. And it's not really obvious why all such things should form a variety or they should have some nice property. So let's start with some simple example. So in this case, d prime is 0, and then d is just d. So if I take a curve and then I consider d points on this collection, so x is curve, then I can consider the cycle should looks like this. And AI is just some rational number, and PI are just point on x. And the summation AI had to be when you sum them together have to be D. So I think it's fairly simple example. And one easy thing to parameterize all such things is you just take a D4 product of X, and then because you don't really care about the order, you don't really care about when Pi appears, so you just look at the symmetric product. Okay. So Chow. I'm not sure the conventional order, so let me just use one here. So D prime first, and then D is just if you look at the symmetric product. Okay. And actually, I think that's work not only just for term, but also for surface or for higher dimensional variety. Dimensional. And it's easy to see in this case, this Chow variety is very easy to describe. It's just a symmetric product or something. And one special thing about curve is this guy is going to be smooth. And if you take X to be dimension 2, so for example, X is the surface, then this guy is not going to be smooth. It's going to have some quotient singularity. And in dimension 1.
Sorry, so here, Chow variety, you really take the variety, not the scheme stuff.
In this case, you can prove. I don't even give the definition of Chow yet, right? So I just some naively you sort of you believe this guy should be the answer. So
That's the one you're thinking about, the variety, underlying variety, not the.
I'm going to introduce the definition later. You just sort of like you know the answer for some example, even you don't know the question, you know the answer. It's just
I know that answer.
Yeah.
Now that's the answer. But we are taking.
I mean, it's also the Chow scheme. In dimension 1, this Chow is there and is also smooth. And in higher dimension, it's not smooth. Not smooth. But it's not too bad. It has some quotient singularity because it's a smooth thing marked out by SN action, or maybe I should say SD action. So that's a fairly simple example, and if you look at this example, it's really not too bad. The construction is very easy. You just take the D4 product and then mark out by some very simple group action SD on this D4 product. So it's not really anything interesting. At least from my point of view, it's not really too complicated. And also one special feature is you don't really care about how 2 points come together. You only remember the end result, like how many points come together. Unlike in the Hilbert scheme case, you really want to know how they approach each other. But in this case, you only need to remember the final result. Okay, so this is a very simple example, and you believe the answer should be like this. Now I'm going to give you the definition for what should be Chow variety. And to do that, let me start with what you want to parameterize. Okay. So let's start with something called well-defined family. So what happened here is there are some tricky issue about if you have a family of cycle, what do you actually mean? And normally what you want is you want a continuously varying family of D cycle. And the issue is how can you make sure this family is actually a nice family? So let's say I start with W. I normally assume it's semi-normal. That's more like for convenience. And later on, by our definition, our Chow variety is automatically semi-normal. And that in characteristic 0 or over C, in the analytic case, I think there's a better way, there's a more refined way to define what Chow variety should be, but I think that's not really our point. So let's just focus on this case. Whenever we talk about Chow variety, we only work on semi-normal set. And if you don't know what semi-normal is, then just remember this picture. That's semi-normal. And that's not semi-normal. Now I'm going to explain what semi-normal is. Just assume it's some nice similarity. And I have a family. Let's say I have a family S over, unfortunately I use S as a notation. I have a family S, I have a family of variety over W, which means I want it to be each fiber is D1 dimensional. So I think that's a very basic condition. I want for each W0, the fiber had to be D1 dimensional. But that's not really good enough. That's just a very wild thing. And when I say well defined, what does that mean? You can imagine the following situation. It's just like when you do calculus and you do two-dimensional thing and you want to take limit. One thing of taking limit is if you let x, y go to 0, 0. And in calculus case, there are some very tricky issue about when x, y go to 0 and what should be the answer. And one easiest way to figure out it has no answer is if you take different direction and the answer are different, then there should be no limit. And what we are going to do is something very similar. So, we want so for each W0 in this W, okay. So let's say I have W here. When I have this kind of family, and I can first assume W is irreducible, so that makes sense easy. And I can take a W0, that's going to be open in W here, and such that S restrict to W0 is flat. So you can use the generic flatness and then assume it's nice on this open set. And once it's flat, it's very easy. Then the fiber should be just perfect. And when it's not flat, then you don't really know the actual answer. And when we say it's well defined, that means if you take any point, and it may not be on the flat locus, but it's okay. You take any curve passing through this point, and the general point of C is in the W0. So I take a curve, and you can make everything more algebraic or more correct using the DDR or whatever you want. And general point. And also W0. So something like this. I have this W0. And the I have two W0. One is lower subscript and one is upper subscript. This one is the open set. I want this curve to be in this open set, and I think it's not a good one. So something maybe nicer is like this. So I pick a point that may outside W0, but it's okay. I choose any curve, and as long as the general point of this curve is in W0, then I take this. And one nice point of this is I can, because I know what's the correct fiber over every point on W0, so I can take this. So what I mean is I take any W prime and then I look at a pullback. And there are some simple procedure to do that, but I think the important thing is to just remember, each time you give a curve in this case, then you can take a limit of this guy. And the point is all the limits should be the same. Okay, so we'll define is this looks complicated, but later on I'm going to give you one condition, then we can try everything you need here. And there's one technical way of saying it, but let me not go to there. Let me just make it sort of vague. And in characteristic P, there's a more technical assumption. You want this limit to be some cycle defined over KW0. That's what we hope. But there's a problem here. If you impose this condition, then some natural universal family is not going to satisfy this condition. So the problem is you want this limit to be defined over the purely inseparable closure of KW0. So that will cause some problem in classic characteristic. But in characteristic 0, you just don't need to worry about this. And one simple thing that make everything like this work is if W is normal, every family. So it's a very, very weak requirement. So somehow you don't need to worry about everything like here. And this condition really just means if I have two components of W, and when I take one component and I get a limit, and I take another component, I take another limit, I want them to be the same. Like you want each W0, there's a corresponding correct fiber of it.
Sorry, your counter example in the number book.
This case, or you mean? I think that is some family that's not well defined, but I don't really have an example because we don't want to camouflage that. I mean, unfortunately I don't have a handy example.
Another question is, if you assume it's well defined, and you take a two-dimensional base,
Yeah.
and can we define a limit procedure on this two-dimensional base? And will we get the same?
No, I mean the reason I use a curve is because I know how to define limit for one-dimensional case.
So two-dimensional.
The problem is I want to. Okay, so suppose the natural thing is I pull back the whole family, but the problem is this one may not be flat. But now because I'm over one-dimensional thing, I just mark out the torsion thing. Then there's a very simple fairness criterion over base is dimension 1, as long as every component is normal. So I just mark out the torsion thing. So it's easy to get a natural family here and which is flat. Then I take the central fiber. That would be my answer for this thing. And if you do the same for surface, I think probably you can do it, but I don't know how to do that in the unique way. But anyway, I mean, just like in calculus case, if along every curve the answer is the same, I think it should give you limit. So you probably don't need a surface thing, right? Because you only need to you only need just a very simple example. Like I think you must know this example. How do you know this one has no limit? You just take x equal to ty, and then the answer depends on t. But as long as you don't have this phenomenon, I mean, you can certainly find example of what I say in this case. But okay, so there's some tricky issue about what we want to parameterize, but let's assume there's no such problem. So let's talk about how to construct your Chow. So now we are assuming we have no issue about what family we want to parameterize. That's actually a big assumption. You really need to go through certain things here. But let's just assume we know what we want to parameterize. So how to construct? Chow varieties. So that's a very classical and way to do it. And to make things easier, let me do it in Pn. So I'm going to assume my ambient space X is Pn, and I'm going to talk about the degree D prime cycle. So now. And I'm going to change the. I'm going to change the notation. Let me change the notation to, and then let's say D prime is R, and then D just the degree. So how do I parameterize an R dimensional cycle in Pn? If you look at the simplest case, if R is n-1, if you want to parameterize 4-dimensional cycle, that's fairly easy. You can just do it in the following way. You just write down the equation for this R. R-1 you just write down the equation for n-1 dimensional thing. That's just one simple equation. And you parameterize that equation. And you may want to mark out the equation by some scalar, or that's up to you, but I think it's really fairly easy to compute that. If R is just n-1, then we can parameterize the equation. So each n-1 dimensional thing in Pn is parameterized. If you want degree D, then it's parameterized by degree D homogeneous equation. I think that's very easy. So you just write down the equation. For example, if you look at n equal to 2, and then D equal to 5, I think 5 is probably too big. It's out of my memory. Maybe make equal to 1. Okay, you want to parameterize all degree 1 thing, and in this case it's really bad because there's no degeneration at all. Then you just look at A0, A1, A2 will give you the answer. Because they just correspond to A0, Z0 plus A1, Z1 plus A2, Z2. So Z0, Z1, Z2 are just homogeneous coordinate of D2. All possible combination of A0, A1, A2 is will give you answer. So that's very easy. And if you have higher degree, then all this AI will be, you would have more AI, but I think it's not really too much trouble. So the key point is if you have co-dimension one thing, then that's really determined by one equation. And you want to mark out by scalar, I think that's really not too big issue. So it's fairly easy to parameterize it in this case. But in general, how are you going to do this? And so let's move on a little bit to co-dimension 2. And assume you want to mimic this, and you want it to be defined by 2 equations. Then you have a very big issue. Because not all co-dimensional 2 are complete intersection. And even if one member is complete intersection, the nearby member may not be complete intersection. So you have some big issue about using this. So here is a very classical trick to get this. We are going to go from an R-dimensional cycle to some equation. So I think that's this has a match. I'm going to introduce something called Chow form. So Chow form is really like I want to get something like this homogeneous equation in some other space. Okay, so how are we going to do this? So here is a simple observation. If I have a R-dimensional thing in Pn, So the codimension of this guy is going to be n minus r. And if I take n minus r plus 1 hyperplane section, then in general they are not going to intersect anything. Some key observation. N minus r hyperplane section. Then in general, we are going to get finitely many points. So just if I take h1, h2 to hn minus r, and then intersect with b, then it should be just finitely many. And of course, then you have to avoid some degenerate case. And what we really need is I go one step further. And if I take h1 to, so this one you don't really like this because you have to be very careful about which h1 you take. Because if you, for example, if you take h1, h2 to hn minus r to be all h1, then it's, of course it's not going to be finitely many. And the number of this point should be the degree of, the h degree of v. I think this is just a classical geometric fact. You take h1, h2 to hn minus r, and then I add one extra section. Then for general choice of this, then the intersection should be 0.
Sorry, if you take n equal to 3, r equal to 1.
N equal to 3, r equal to 1. So it's one dimensional thing in P3.
Yeah.
Then you, in this case, so n minus r in this case is 2. So if you take 2 hyperplane sections, then you have 0 dimensional set. The respective dimension is 0. So you have one wait.
No, yeah.
Oh yeah, I think my number is wrong. I think it's just r.
Oh, and r plus.
Yeah. Sorry. I mean, you know that, right? So just some number. Don't worry about whatever. Yeah. Just some number. And yeah. Right. Yeah. I mean, you always confused about dimension and codimension. So anyway, in this case, in general, that should be empty. And so all possible collections to make them non-empty, I'm going to claim is a divisor.
Yeah, the last one will be the B, right?
Oh yeah. Alright. So I fix a V. I'm going to. Okay, so like this, I start with some V, which is D R dimensional. So I fix this V, and I want to see how can I associate a divisor to V, in a divisor in some other space. So a divisor just normally means a form or whatever you will see it later. So for this V, I'm going to take what kind of thing I'm going to get. And what I'm going to get is I just take all possible h1 to hr minus 1 such that the intersection is non-empty. You know, in general, it's going to be empty. And each choice of HI is in Pn dual. So So let me just use Pn, but you can, the more precise way is Pn q. So I have Pn q, and because I take r plus 1, so I have to times it by r plus 1. So if you count the dimension, that's n times r plus 1. The ambient space is this. And for it to be non-empty, it is a divider. So let me just do one simple example and to convince you that's the correct. The whole point is the new space is this. And I'm going to say whenever I have a V, I'm going to have some point here which correspond to this non-empty, and all these points form a divisor here. So that's a simple example. I start with x equal to P2, and V is a curve, so R equal to 1. So in this case, I have to take 2, and in our case, I have to take P2 0 times P2V. So I have to choose H1 and H2 to make H1 intersection H2 and intersection V to be 0. And now consider the incidence variety. I have V times P1 P1 times P1 P1. I'm going to compute the dimension of this set, and this should be in this case. That's not P1. The ambient space would be going to be 4-dimensional. So if I want it to be divided, then it has to be 3-dimensional. So the end result has to be 3-dimensional. Unfortunately, I think I'm not going to say anything about RCP. So the incidence variety is I take any point x which is on V, and I take any hyperplane H1 and then H2, and such that so I want x to be on H1 and x to be on H2 and x to be on V. So that's just some subvariety in here. And I want to compute, what I need is I do the projection to, let me write here. There's no space. X is in V, x is on H1, and x is on H2. I have two natural projections. One is forget the other two factors, and the other is forget the first factor. So now let's compute what's the same here, what's the incident variety in here. Let's count the dimension in this one. I pick any x on V, and V is 1-dimensional, so you have to remember you have to add 1 later, because you have a freedom of 1 dimension to choose x. So you pick any x, and then you look at all possible H1 passing through x, which is a P1, so it's 1-dimensional. And you also look at all possible H2 passing through x, that's also a P1, so it's 1-dimensional. So for each x, that's 2-dimensional. And because I say you have a choice of V, of x and V, that's 1-dimensional, so the total is 3-dimensional. And so you only need to say projection here in general is going to be finite, then you are done. And as you can see, if you take two general hyperplane sections, then they are going to intersect with V at finite dependent point. So the fiber of this guy is, in general, is going to be finite. So you can see that the image of this guy here is going to be 3-dimensional.
Do we have to worry about if it's a pure dimension?
I mean, that's just a I think you can handle it with for V reducible, then I think everything has to be reducible. And for V, if V has you have different component, because each component will give you the same dimension, so I think it's fine. So you need, I mean, if V is reducible, then the image here has to be reducible. Is that true? I'm not sure, but if you have no objection, then I'm going to assume it's true. I think it's not really too hard. You probably need a little bit more to work, but I think it's not too hard to imagine what the computation I did, you can do it family-wise, so I think it's not really a big problem. So let me just go back to this class. So whenever I have an R-dimensional variety B, then I can associate a divisor in this big space. And this ambient space dimension is n times R plus 1. Okay. So I'm going to code it. And as I also mentioned earlier, although I use only Tn, but in principle it doesn't really matter. If you have a divisor here, then you should just get some sort of homogeneous form. And if you have Pn times some fiber product, then it's some sort of bihomogeneous or R plus 1 homogeneous. It's not really a big problem. You will probably need to do some exercise to get familiar with this, but in general, just imagine it's a form in some higher dimensional variety. So in principle, it's a divisor and some higher dimensional variety, and you get an equation. So the whole point is for every variety with the correct dimension, you are going to get some form there. And there should be some nice answer about this. And let me just give you one example. That's a very trivial example, but I think it's nice to have some concrete calculation. How about if I take the R to be 0 and X to be P2? So that's another example. X is P2, R is 0. So and I take my point V to be just the point 0, 0, 1. Great. So I just take the V to be 1 point. And what's the incidence variety in this case? So I have to take all possible hyperplane tests into this. So all possible hyperplane looks like A0, A1, and A2. And each corresponds to A0, Z1, Z0 plus A1, Z1 plus A2, Z2 equal to 0. And because 0, 0, 1 is on here, so that just means A2 is 0. So what I get is just a P1. That's on P2. Oh, that's the same as P2. So for this point, 0, 0, 1, I get P1 in there. And this P1 it's not really too hard to write down. Okay, so the 0. Unfortunately, this is really not too much time, so let me just mention the 0. So for each, now I'm going to take D prime and D notation. Okay. So for each D and D prime, so I fix the dimension D prime and I fix the degree D is going to be objective. So the first thing is this. And the second thing is, because I'm always on a semi-normal category, normally there is going to be a from Hilbert scheme to Chow variety thing. But because I'm always, in this definition, I'm going to assume it's something semi-normal. So to get a morphism from Hilbert scheme to Chow, I need to take some normalization. And unfortunately, there's a let me just use this also, but it's not really a good notation. So suppose I fix the Hilbert polynomial. then I can look at the Hilbert scheme. And this Hilbert scheme by no means would have nice singularity. So to make everything better, so I have to take the same line normalization. And then I can forget the scheme structure. Not really the scheme structure, I can forget how they come together. And then I look at this. And then here, there's a Hilbert to Chow morphism. And this morphism is projective. And in many nicer cases, it's going to be a really nice morphism. It's almost the same, but I think you need to impose extra condition, so let me not go to that. And other thing is in heuristic P, we don't have really a Chow scheme. We need extra pair. So let me mention this in here. So on this all well-defined family, I have some extra thing, and I have 3 possible things here. The first thing is just some sort of functor. I want to parameterize whole family. So this I want to parameterize well-defined family over Z. And then I have the more natural Chow thing. That's just I want to parameterize well-defined family. And with I'm going to say something that won't make any sense to you for now, but you just memorize that. And I'm going to oh no. Sorry. And then I'm going to define something here. That's going to parameterize well-defined family. And in positive characteristic, only this guy is going to be a functor. And it's going to be coarse represented by some scheme, and we are going to call it Chow scheme in that case. And these two are, in general, are not going to be functor. Not going to be functor means that if you have a family, it's not really makes sense to pull back in all cases. In some cases, you can pull back family, but not in all cases. In these two, then you cannot always pull back. And this one you can pull back. But this one is not going to be a fine moduli space unlike this. It's only going to be a coarse moduli space. But this guy is going to be still smooth projective. And wait, when should I stop? 10? Okay, so I said 10. Okay, so now I can expand this. And one bad thing is the universal family and positive characteristic normally appear here. So you really have some problem. You have some, if you stick with Chow small, then you have a functor and it's represented by a coarse moduli space, but you don't have a universal family. And if you go to here, then this universal family, I mean, when we say universal family, it's really not really a nice terminology. We want it to be, you can pull it back and you can manipulate this family at all. But in this case, you have some issue because you cannot always pull back. So let me write it down.
So sorry, before you say positive characteristic, so this Chow variety has a universal family?
Yeah, because it's a fine moduli space.
Oh, this is fine family.
Yeah, it's a fine moduli space.
Could you say one word? How do I see the original V from the Chow form?
Original B?
V, yeah. Is that clear? It's a 1-1 correspondence?
I have an example I erase, right?
Yeah, that
I think it's complicated.
but it's a theorem saying it's a one-one correspondence.
That's a one-one correspondence. If you want to parameterize this V, it's
Yeah.
the same as parameterize cycle. It's the same as parameterize divisor or forms in this larger space. And that's a one-one correspondence. And that's how they make it become a fine moduli space. They construct this thing. That's which is very easy. Once you have just form, it's very easy to parameterize. And you can prove that's actually a one-one correspondence. And unfortunately, in positive characteristic, then there's some problem with so let me, in the last 5 or 10 minutes, let me give you one example, and that will demonstrate the problem. Let's move back to Chow variety of the dimension 0 set. So let's say we are in characteristic 2. Our space is x equal to A2. Now, you should believe this guy is the universal band. Right. I mean, in characteristic 0 is obviously the universal band. And this guy should be the Chow variety. Now the problem is, if you think about this family, it's actually okay outside diagonal. I mean, if it's outside diagonal, it's just 2 different points, so there's no problem at all. And if it's on diagonal, it's just 1 point, but with multiplicity 2. In this case, because we are, this 2 is not characteristic 2, it's just degree 2. And unfortunately, that's a coincidence here. So I just take degree to be 2, and in characteristic 2, and then that. And what's the problem with this family on diagonal? So if you look at this family and then go back to diagonal, then let's look at the pullback. If we just do the non-E pullback, I just pull back a family to A2, what would going to happen? We expect to get something that's multiplicity 2, but we are going to get something that's degree 4. If you do a pullback, so we are in this case. I have coordinate x1, y1, which is the first point coordinate, and then x2, y2, which is the coordinate of the second point. And what's this guy? What's the symmetric product? When you do a symmetric product, then what you get is you mix x1, you mix 1 and 2. So on this coordinate, x1 plus x2 have to be, if you so you want to look at all possible polynomial, and when you exchange 1 and 2, it remains the same. So I think just some simple calculation. So, and what else? Yeah, that's why I need this. That's really easy to compute, just I don't remember the answer. Yeah, x1, y2 plus y1, x2, x1, y1 plus x2, y2, and then x1, x2, y1, y2. You can compute this. If you exchange 1 and 2, and what remains the same is generated by this. And if I pull back to diagonal, that just means I want to set x1 equal to x2, y1 equal to y2. And what would happen? In this case, x1 equal to x2, so that's 2x1, and that's 2y1. And but I know in characteristic 2, so that's 0, that's 0. And this one is x1. I think that's also 0. I think almost all are 0, except the last 2. That's x1 squared, y1 squared. So if you look at what happened on the diagonal, the pullback of the diagonal, it's just let me get. So the pullback is just unfortunately I use UV instead of X1, Y1. And here when you pull back, then it just X, KUV, that's not really an issue. So what you get is this and over spectrum. Okay, U square, V square. Or if you want, I think use X1, Y1. Make for check. And unfortunately, that's degree 4. I mean, everyone should see is actually degree 4. So you have to make a choice. And actually, you can make 2 choices. So if you just look at this family, and you do the very, very naive pullback up from diagonal, then what you get is not the correct family. So there are some issues here. So that's why I need to take limit. And if you think what the problem is, because every member here is under non-flat locus, so this cause some trouble. And if I have time, I'm going to tell you what's that mean. Okay, I have 2 minutes. So let me explain what this condition is. First, Chow field definition. That means when I look at each Z0, I look at the corresponding fiber. And I can look at the Chow form. This condition means if the Chow form is the coefficient of this Chow form is defined over KZ0, then I say is with Chow field condition. And what's this condition? That just means I want this cycle, and I mentioned very, very early in the in this lecture, I want a member to be defined over the purely inseparable closure. If in that definition I can make the cycle to be defined over KZ0 already, then I say it's satisfy the field definition. So as you can see that these 2 conditions are really not easy to see geometry. It's necessary, but it's probably not really easy to see in a geometric term. So anyway, you just remember there are some problems in heresy P. And also remembering heresy P is not really a fine modular space, it's just a closed modular space. But if you look at the end result, it's still projective. So, and let me stop this.
Chow field condition is pure inseparable.
Chow field condition means okay, so this. So suppose I have a family. And for each point, a well-defined family means I have some correct member here, right? So let me call it as 0. And Chow field means that if you do my construction earlier to get a form, then the coefficient of all this form is over K0. And the field definition means this cycle is defined over K0. And obviously, if it's defined over K0, then all the coefficient of this form is going to be defined over K0, but not the other way around. So that's a weaker condition, that's a stronger condition that require more on the particle family. So that's why you can pull back. Like this family, you cannot pull it back. Like, yeah, it's also easy to see. You cannot pull back to diagonal for this family because you just get something wrong. Yeah. And to make it a funter, you have to have pullback property. Whenever you have Z1 to Z2, then you can pull back a family over Z2 back to Z1. And I think if it has a chance to be represented by a scheme or by an algebraic space or whatever, then you need to have this property. But this guy or this guy don't have that property. You cannot do pullback all the time. You have to be very careful about what you can pull back. And if you stick with this one, then you can pull. But as that example demonstrates, if you stick with this one, then some nice family is not going to follow. So there are some.
Any other questions? The last
这个 SD 是敲破的，
对，
link 是在
不，我这是一个 cycle 嘛，对，它一个 cycle 可以得到它的敲缝。